In this lesson, we're going to look at the graphs of the sine and cosine functions. Let's start by discussing some of their properties. The domain of both of those functions, cosine and sine, is all real numbers. You can plug anything into it, and the range of both is also minus 1 to 1. If you're unfamiliar with what they look like, here's a simple graph. You can see that they both reach a maximum height of 1, a minimum height of -1, and they have a pattern that just repeats, and in fact they're the exact same pattern, the exact same wave. It's just been shifted, right? The sine function goes through the point 0, 0, whereas the cosine function goes through the point 0, 1. So one is just a phase shift of the other. Well, these are what we call periodic functions because they repeat on a certain period, right? The true definition of a periodic function is the idea that if you add a given amount to x, right, f of x plus p is just going to get you back that same answer you have when you put in x. And we always let p be the smallest value possible. So if there is a period, you let p be the smallest thing, because if it's a period, it'll keep repeating. For sine, that happens every 2 pi. And for cosine, it also happens every 2 pi. So if you add 2 pi, 4 pi, 6 pi, 8 pi, right, any multiple of 2 pi, you'll get the exact same answer that you would if there wasn't anything in there, right? Sine of t plus 2 pi is the same thing as sine of t, and sine of t plus 8 pi is also the same thing as sine of t, etc., etc., etc. And since 2 pi is the smallest one, that's what we call the period of both of those functions. So if we want to kind of generalize, put it all in one place, we can see side by side, same domain, same range, same period. The big difference are the zeros. The zeros of the sine function happen at every multiple of pi. That's what n pi means. N is just an integer. So you'll get a 0 out of the sine function every time you put in a multiple of pi. However, for the cosine function, remember it's been shifted, so it's every multiple of pi plus pi over 2. So they write it this way, but really it's still a multiple of n pi, so 1 pi, 2 pi, 3 pi, 4 pi, but each time you have to add pi over 2. So 1 plus a half, 1.5 pi, 2 plus a half, 2.5 pi, etc., etc., etc. Those values will always give you a 0 answer. And then the other big difference between the two is that sine is an odd function. Remember, an odd function means if you plug a negative number in, you get the opposite answer you would have gotten if you plugged the positive number in. Whereas cosine is an even function, so cosine of a negative number is the same thing as cosine of a positive number. It's like x squared, right? So this is like our x squared function, whereas this one's like our x cubed function, even and odd. All right, how about graphs of these things? Well, I already showed you them together on the same graph, but let's look at them individually a little bit more closely. You can see that the pattern keeps going. The sine function hits 0, 0, and then it zeros at all of those pi's, right? We talked about it gives you an answer of 0 at every multiple of pi. So it hit again over here at 3 pi, and down here at -2 pi, etc., etc. Height of 1, a low spot of -1. Cosine function, same shape, height of 1, a low spot of -1, but instead of going through at every pi, you can see it's every pi plus pi over 2, right? So here's 0 plus pi over 2. Here's pi plus pi over 2, so there's 1.5 pi. Then 2.5 it would hit, right? 1/2, 1.5, 2.5. Okay, very simple. Well, finding the amplitude and period of what we call sinusoidal functions just means functions that have a sine curve, wavelength to them. Their sine, their shape looks like a sine curve. Well, a couple things. when we're talking about amplitudes, we have to identify high points and low points. So the high point here was up at 1, the low point here is at -1. High point here, right, up at 1, down at -1. There's an actual formula for calculating amplitude. It's very simple. The book kind of glosses over it because with sine and cosine, our amplitude is simple. It's 1. But I don't want you thinking that it's 1 because that's the high point. The actual formula for amplitude, so amplitude equals 1/2 max minus min. So for both of our curves, sine and cosine, we get 1/2, the max is 1, right, minus the min, which is -1, 1/2, 1 plus 1, 1/2 of 2 equals 1. And so there's our amplitude of 1. It's half the total distance between the max and min. That's what we're doing. Half the total distance, right? Because max minus min just gives you the range, the difference between those two numbers, and then we're taking half of that. That's what your amplitude is. So with the sine and cosine, your amplitude ends up also being the maximum value it gets because these functions are centered on the x-axis, right? They're the same height above as they are below. But if we shifted that function up, shifted it up above the line or shifted it down below the line, it would still have an amplitude of 1. Okay, so the amplitude has nothing to do with its maximum value other than the fact that you plug it into that formula to actually find the amplitude. Okay, but they're not always going to be equal. When we look at our functions in a more general case, and we put an a in front of it and a b on the inside of it, then a ends up being the amplitude. Because if the sine function, right, look at the sine function all by itself. So if the green part keeps spitting out numbers between -1 and 1, then if each of those answers is multiplied by a constant a, then it's going to spit out numbers between -a and a. And therefore a ends up being the amplitude, because back to the formula, the amplitude is going to be 1/2 of the high point, which in this case is going to be a, minus the low point, which is going to be minus a, right? And we get 1/2 a plus a, 1/2 2a, which is just a. So any constant you multiply in front of the sine or cosine function will always become the amplitude. Here's an example. If we look at the first one, 3 sine x, we can all see very clearly that 3 is our amplitude. Second one, 1/3 sine x. 1/3 is the amplitude. And the last one, sine x, the amplitude is 1. If we needed to graph these functions, if you just remember what the basic shape of them, of what the basic shape is, you're just stretching them, right? These are vertical stretches. Remember before when we multiply by a constant on the outside of the function, it's a vertical stretch? Well, these are vertical stretches. So there are your vertical stretches. Multiply by 3, and now it goes up to +3 and down to -3. Multiply by 1/3, and it's technically a compression, right, because it's smaller than 1, but it's still a vertical stretch. It's just a vertical compression. Okay, what if we put a negative number in front of these functions? Well, what happens when we multiply any function by a negative number on the outside? It gives us a vertical flip, right? It flips top to bottom. But because these functions are symmetrical, when you flip them top to bottom, they pretty much look the same. So there's the -2, right? The 2 stretches it up to a height of 2, and then the negative flips it. So it ends up looking the same. It's just, it almost looks like it's been shifted. And so you'll notice that if we started with the blue line and then shifted it over, wouldn't we also get the same thing as the red line as we do from flipping it? Yeah, so shifts and flips are going to end up giving us similar looking graphs because of the repeating, right? The repetition, the period of these functions. Okay, how about if we need to graph these things? So let's try and graph or sketch one cycle of y equals 3x and y equals sine of 1/3 x and just the standard y equals sine x. You always want to start with the standard, just like we always started with the standard x squared and then figured out what the shifts and stretches were when we had a quadratic. Start with sine x, divide its period, 2 pi, by 3 to get 2 pi over 3 for sine of 3x, right? The rule is whatever a is, sorry, this is our b, sorry, a goes in front. Whatever our b is, right, you take the original period of 2 pi and divide it by b, and that gives you your new period. Because if this function repeats every time x gets up to 2 pi, if you're multiplying all of these x values by 3 before you're evaluating the sign of them, then this total number is going to get to 6 pi by the time x gets to 2 pi. And so we will have gone through our period 3 times, right? It would have gone 3 periods, which is why if you take 2 pi and divide it by that number, you get the actual period of 2/3 pi. So now we know that one cycle of this function will happen in just 0 to 2/3 pi instead of all the way up to 2 pi. Now the original function, if you didn't pay attention to the graph, and I don't blame you if you didn't, we can look at this one. Doesn't matter if we look at sine or cosine because they look pretty much the same. Let's go up and look at a sine one just so you can see it. From 0, right, to 2 pi, there's our period, that's where it repeats. We have 4 chunks where there's important stuff, right? We get a max that happens here. We cross 0 here. We get a min that happens here, and then we come back to 0 there. So you see how we've got 1, 2, 3, 4 pieces, right? We cut it in half and we get where it hits 0. Cut each of those in half and we get the max and mins. So you always want to take these functions and think of them in 4 pieces. Take our period of 0 to 2 pi over 3 and cut it into 4 pieces. Divide it up into 4 equal parts. So 2 pi over 3, right, times 1/4 is 2 pi over 12, or pi over 6. So we know each of those quarters happens every pi over 6. So we go 0, pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, right? And then finally 4 pi over 6, which gets us back to 2 pi over 3. There are the 4 stops, right? And it ends up giving us 5 total if we count the first piece. We can do the same thing with the second function. Now take 2 pi and divide it by 1/3. Well, when you divide it by 1/3, you really end up multiplying it by 3, and now you have a period of 0 to 6 pi, and we could do the same thing, cut that into 4 pieces. Here's what they end up looking like. The blue one is the normal one. The green one, right, is the one that's been multiplied by 3. So you can see how it's repeating more quickly. If we continued this pattern, it's going to have a maximum here, right? Sorry, a maximum here, and then cross here, and then a maximum here, cross there, right? It's going to repeat more quickly. By the time it gets to here, 2 pi, you will have had 3 of these instead of 1, because it's now going 3 times as fast. Just like the red one, when you get to 2 pi, you've only got 1/3 of it, and then another third, and then finally it finishes off at 6 pi. But if you take the 0 to 6 pi interval and cut it up into 4, so that's a distance of 6 pi, you just do 6 pi over 4, which gives you 3 pi over 2, and it's 4 quadrants, right, or every 3 pi over 2, so here's 3 pi over 2, and then 6 pi over 2, which is 3, right, and then 9 pi over 2, and then finally the last one, 6, and you can see there's your max, where it hits, minimum, where it comes back. So that helps you just to draw the lines. What if we want to graph something that has both a stretch and a horizontal, phase change in period? Well, it's simple. You're still going to use the trick of taking your period, dividing by b, right? This is your b, which gives you the new period. Take that new period, cut it up into your 4 quarters. So take 4 pi divided by 4, and you see that it repeats every pi, or that's your pieces are every pi. So now on your graph, you know that every pi is where something's going to happen. There's your 4 periods, right? Starting at 0, then pi, 2 pi, 3 pi, 4 pi. You know that it hits here, here. You know that it's going to be a minimum here, and a maximum here, and a maximum there, because we're now dealing with cosine. And now all you have to do is figure out, well, what are those max and mins? Because a is 3, that gives us a height of 3, right? A period, or an amplitude of 3. So we're up here at 3 and -3. I mean, technically, this looks exactly the same as the other line if you just would have written a 1, right, and a -1. So that's all that's happening, is the scale is changing. We can change the amplitude and period of these functions very simply. As we've seen, the period is always going to be 2 pi over b, whatever b is, and then the amplitude is always going to be the absolute value of a, right? Because if we put a negative number in there, we would still consider the absolute value to be the amplitude. So there's the general case. The amplitude is a, the period is 2 pi divided by b, whatever b happens to be, even if it's a fraction. If you divide by a fraction, it just gets bigger. Sine and cosine, this is the sine one. Remember, sine starts at 0, 0. Cosine starts at 0, 1. Same thing. Amplitude is now a, period is 2 pi over b. Last but not least, we can do phase shifts, right? We've looked at vertical shifts. We've looked at really kind of a horizontal, we looked at vertical stretching. We've looked at horizontal stretching by changing the period. Now we can look at horizontal shifts left and right. And just like any other function, you get shifted left and right by putting numbers inside, right? Adding and subtracting numbers on the inside of the function. X minus c, or x minus c for cosine. So we're putting it on the inside. Well, if we know what sine looks like, and we know sine starts at 0, right, the blue one here, starts at 0, does this. If we do x minus pi over 2, that means we're just shifting to the right. Remember, it's just like before, x minus c, then you're shifting to the right by c units. So everything gets shifted over to pi over 2, and now you start at pi over 2 and go to 5 pi over 2. That's just pi over 2 plus a half. And then everything looks the same. If we want to graph something that has all of these shifts, still the exact same thing we've done before. Start with the regular function and then describe what happens. The first thing you want to do, identify the amplitude, which is very simply just the absolute value of the number in front of it. That tells you how high it's going to go and how low it's going to go. Then you figure out the new period by doing 2 pi divided by whatever your b is. Then you recognize your phase shift, and you know that you're going to shift that. And then you just start by thinking of this as your new period interval, right? Instead of going from 0 to 2 pi over b, you're going from whatever c is to c plus 2 pi over b. You can take that starting point of c and add your pieces to it, right? Remember, whatever 2 pi over b is, you cut that into 4 pieces, and then you can add it to c to get your 4 critical points, and then figure out, okay, that's where it's 0, that's where it's up, that's where it's down, etc., etc., etc. Right? They're going to walk you through this with a lot of letters that's going to make your head hurt. We might as well just look at an actual example and see how we can do it with an actual example with some numbers. Okay, so here's a good example. Just like before, first thing we want to do, identify the amplitude, because it's got a negative 1 in front of it, right? A negative sign just means negative 1. Our amplitude is 1. Next thing we do, we recognize that we have a 2 here. That's our b, right? b is 2. So we have to do 2 pi over b, or 2 pi over 2, or we now have a period of pi, repeats every pi. Third step, identify the phase shift. In this case, remember, it's x minus c, so c ends up being a negative. Oh, that was a bad color. Let's get rid of that. C ends up being a negative pi over 2. And so instead of going from 0 to pi, you go from 0 minus pi over 2, right, which is just negative pi over 2, to pi minus that. So here's your new interval. Negative pi over 2 to pi over 2. Still has an overall length of pi. So if you take pi and divide it by 4, that's the size of each of those 4 important pieces. So you start at negative pi over 2 and then add pi over 4 to it. So this is 2 pi over 4, right? So now this is negative pi over 4. Right, because we're adding from a negative a half, add a fourth again to get to 0, add a fourth again to get to pi over 4, add a fourth again to get to pi over 2, the end spot. So there's your 5 important pieces. Now all you have to do is graph those, right? So here they're just showing the same ones that we found. Graph those. Here they are. Right, the points on the graph, and then figure out what happens at each of those places. Cosine is normally at, where does cosine normally start? If this is the start, remember this is the beginning of our period, cosine normally starts up at 1, 0, right? If you put in 0 cosine, you get 1. So you start up here at 1, and then it hits, goes to minimum, hits, goes to maximum. That would be the normal cosine that's just been shifted over. But the last thing you have to worry about is this flip, right? The true thing we're trying to graph has that negative, so it gets flipped. And that's why you end up getting the red graph. And so that's all you have to do to graph these functions, right? Go through those steps, very simple. First you identify your amplitude, then you identify your b, right? Figure out what your period changer is, if you want to call it that. Then figure out what your new period is, divide that by 4, get your critical spots, put them on the graph what the function would look like, and then take care of any flips that you have to worry about. How about if we're just given a function and asked to figure out what the period and phase shift are? Well, this doesn't help us written how it is because we need something written as a, right, a times x minus c. So all you have to do is factor that 3 out, right? Sorry, I should have written this as a b, remember, because this is the b on the inside. So there's my b, there's my x minus c. The a is the thing on the outside, so that's my amplitude. This is now my period changer, right? So 2 pi divided by that gives me my new period of 2/3 pi. And then once I've distributed this out, I can now see that this is c. That's my phase shift. What about the next one? Again, it's not written in the form that we need. We need a sine of b times the quantity x minus c. So we have to factor out this pi. And this would have just been plus 2 over pi, but then they already made it a minus to put it into this form of the minus. We see that 3 is our amplitude. B is pi, so our period is now 2, right? And our phase shift is negative 2 over pi. And I know that feels weird, but pi is just a number, so we can do negative 2 divided by pi. If we wanted to graph something of this form, we have to do what we just did and rewrite it in a form where we can recognize B and our phase shift. They call it K. I often call it C. You know, A, B, C kind of makes sense. All right, so there's our amplitude. We can identify that. 2 pi divided by 2. There's our new period. Our starting point, our K, is pi over 4. We take our cycle and we go from 0 to pi and we add everything. So now we're going from pi over 4 to 5 pi over 4. Take your pi, cut it into a fourth, and know that you're going to be adding 1/4 to these things. So you take your 1/4, add it to the starting point, right? And you get 1/4, 2/4, which is a half, 3/4, 4/4, which is just 1, and then 5/4. Put all those on the graph, right? 1/4, 2/4, 3/4, 4/4, 5/4. You know that sine starts at 0, 0, so it starts at 0 here, up to its max, back down to 0, down to its min, back up to 0. There's your function. It's just that easy. And then all you had to do was make sure that when you were doing these max and mins, they were going to 3 and -3 instead of 1 and -1. Last thing we can do, right? We've done vertical shifts. Sorry, we've done vertical stretching, horizontal stretching. We've done horizontal shifts, right, with the phase shifting thing. And then now we can do vertical shifts. And of course now they call it a C. I wish they'd be more consistent. Okay, but just like everything else, everything is still done the same. And just like with other functions, you always do this last anyway, right? You work from the inside out. You figure out what this shift is. That tells you where you start. You're multiplying by this, so you figure out what your period is. Then you figure out what A is to see if you're stretching it. And then the last thing you do is move it up or down. So everything we've done before from all the other examples is exactly the same. In fact, if we were going to graph just this function, it's exactly what we've done before, and that would give us the one in blue. And the last thing you have to do is just move everything up by 3. So take those critical points, right? We started here, 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 and here by taking our period and cutting it into 4 pieces. And then those things all just get moved up by 3. So 0 becomes 3, right? -1 becomes 2. 0 becomes 3, right? 1 becomes 4. and 0 becomes 3. Simple, easy peasy. Don't overthink it. Lastly, we can look at how to model something with these functions. So if we're given a bunch of data and we're told that the data points should be modeled by our sine function, first thing you want to do is plot all the points and sketch it out and give yourself an overall idea of what's happening. Now you look at this and go, all right, that looks like a sine function, right? Because remember, sine starts at 0, goes up, and ends at 0. So this is now going to become my starting point and my ending point. So instead of starting at 0, I start at 1 and I end at 12. I can also calculate my amplitude very easily by taking the maximum value, which was 16.1, the minimum value, which was down here at 8.3, the difference between those divided by 2, there's my amplitude of 3.9. I can also find kind of what the axis is now, right? The midpoint of our amplitude, because we know with sine functions we get equal distance above and equal distance below whatever our axis is. You kind of think of it as an axis of symmetry. So it's going to be halfway in between the max and min. So max plus min, right, divided by 2, we're taking the average of those two numbers, and we get 12.2 as our new horizontal axis. Okay, we're going from 1 to 12. 12, right, that's a distance of 12. 12 is going to be our period. And so we set it equal to that, solve for b, and we get that it's repeating every pi over 6. Plug everything in that we know. We found our amplitude, we found our period, we found our horizontal shift. Now all we have to do is figure out what the, we found our vertical shift. Now all we have to do is find our horizontal shift. So to find that phase shift, right, that horizontal shift, we can substitute the x and y values of the maximum into this equation and solve for c. Why would we choose the maximum? Well, you'll see. Because a maximum value of 16.1, when you plug all these numbers in, right, the first thing we're going to do is subtract 12.2, then divide by 3.9, you're going to actually get 1. And that makes sense because the maximum should happen when the sine function spits out 1. The only reason why we're not getting a maximum of 1 is because this thing equals 1, then you multiply it by 3.9, add 12.2 to it, and that's how you get 16.1. So now you have the sine function is equal to 1. And we know that for a normal sine function, it reaches that first maximum at pi over 2. So we know that if we plug pi over 2 into sine, it equals 1, which tells us all of this junk has to equal pi over 2 because sine of pi over 2 equals 1. So you take all that stuff and set it equal to pi over 2 and solve. Solve for what x is. They made it a c here. Don't let that confuse you. This is still x, right? You're still solving for x. Do the math very simply. Multiply both sides by 6. Divide both sides by pi. That's where you get 3. Then 6 minus something equals 3. And you go, ah, it's 3. So now we have our phase shift. And we finally have the entire equation that is supposed to model daylight hours in Paris. Okay? The last example is different from what we've been doing before. Now it's simple harmonic motion. I wouldn't spend a lot of time on this. It's not that big of a deal. You'll need it for physics, but for us, we're not gonna care about it too much. So we'll just go through it kind of quickly. Simple harmonic motion just means you have something that is modeled by a simple sine or a simple cosine wave, right? A sine of omega t or a cosine of omega t. Your amplitude is A, duh, because that's the number in front of it. Your period is still 2 pi over b, but in this case b is omega, so it's just 2 pi over omega. And then the frequency is just the inverse of that, right? The period is how long it takes to complete one cycle. The frequency is the number of cycles per every unit of time, so that's an inverse. Given a word problem like this, a ball attached to a spring is pulled down 6 inches, released. The resulting simple harmonic motion has a period of 8 seconds. Write an equation for the ball's simple harmonic motion. Well, we have to choose between sine and cosine, right? They both do simple harmonic motion. But because at time 0, right, it's pulled down 6 inches and then released, so at time 0, the answer out of the function should be 6. When you put in t equals 0 into the sine function, you get 0. That doesn't work. When you put 0 into the cosine function, you get a. That works. So we have to choose the cosine one. And because when we pull it down, it's 6 inches down, we set that answer to be -6, which tells us a has to be -6 from the previous one, remember, because this told us that when t equals 0, we get y equals a. And at that point, it's -6, right? It's been pulled down by -6. So now we have a equals -6. That's the first victory. Well, I guess the second victory. The first was realizing that we're using a cosine. Next, we have to figure out what our period is. We know that 2 pi over omega has to be our period, and it told us it repeats every 8 seconds, right? So we set it equal to 8, solve for omega, we get pi over 4, plug that back in, and there is our equation. The -6 that we got on the first step, the pi over 4 that we got on the second step, and that is the function that best models this harmonic motion. That's it, guys.